So, in thinking about measurement systems, units, right? Uh, I always find it funny that people who are fans of the metric system, they're like, oh yeah, no, like the imperial system is bullshit. It's metric system is great, yeah. Metric system is bullshit too, right? The SI system is bullshit. Um, it's pretty easy to see that this is the case because one of its units is the mole, which is actually just a number whose value was completely unknown, like, the fine precision was unknown. The value of the mole was unknown until it was just recently defined. You were like, yeah, well, whatever that extra precision is, we don't care. We just define it at this point so that it's backwards compatible with, former research. Which is, as far as that actually goes, that's a perfectly reasonable, like, yeah, why push for higher precision than this? It was already to a ludicrous degree of precision, and it was consistent with, published science for a very long period of time, a very large, vast body of work. Yeah, okay. I get that. But as far as looking at the metric system, you have the mole as a unit when it's actually just a number whose value was not even known. That's fucking stupid. What? And then you also have what I think the fundamental unit involving electricity is the amp, the ampere, when it should actually probably be, because so the amp measures current, it should actually be, if you were looking at a fundamental uh, unit for electricity, should probably be the charge of an electron, because that is also the charge of a proton and the charge of a W boson, positive or negative of that, and the charge of a positron, and, like, the size of it, the size of the charge is the same for all of these. That is a fundamental quantum thing. Current is a measure of, like, how many of those are flowing through a space over a certain amount of time. Like, that should be a derived unit, not a basic unit. What the hell are you doing? And I totally understand, like, when these units were made, when they were set up as the base units, it wasn't understood. The details of how all this shit worked was not understood, but it is now. So why are we sticking with this shit, right? You look to, like, oh, pounds and miles and things. It's like, oh, those are weird numbers. Yeah, those numbers are actually not anywhere near as weird as the speed of light in meters per second. That number is nonsense. Or Avogadro's number, which is basically the number that is the unit mole. Fuck me. Yeah, so there's issues. There's issues. I mean, clearly it works. Clearly it works. So, you know, I'm just whatever. Ignore everything that I'm saying because it doesn't matter. It works just fine. Obviously. Do whatever the fuck you want to do. Right? But, just kind of playing around with, like, how to make a better mousetrap sort of shit. When we have a perfectly fine mousetrap that millions upon millions of people, billions of people, are perfectly happy with, we don't need a better mousetrap. But, okay. So my idea is kind of start with, let's clean up the numbers a little bit, right? So metric is mostly base 10. Okay. It's a terrible choice of base because it doesn't have very many nice factors, just 2 and 5. Basically, the fact that you have 2 hands and each one has 5 fingers, that's all that's happening there. It's not very pleasant. 4 doesn't go into it, 3 doesn't go into it, 6 doesn't go into it. There's a number really close to 10, though, where all that shit goes into it. And that's 12. And it's not, I don't think it's a coincidence that there's 12 hours on the face of a clock, and there's 12 inches in a foot. And, 12 has nice properties. You can cut it in half, you can cut it in 3, you can cut it in 4, and you can cut it in 6. 8 is pretty easy. It's easier to cut 12 into 8 than it is to cut 10 into 8. It's not too hard to cut 10 into 8, but it's easier to cut 12 into 8. 9 gets along with 12 better than 9 gets along with 10. So while 8 and 9 don't go into 12, they cooperate with it to a pretty nice degree. 10 even kind of cooperates with 12 pretty well. So 12 is a better base. And kind of as we're counting up, looking at the at the factors, really the only thing we're missing is 5, right? 1 works, because you can take all of the 12. 2 works, you can cut it in half. 3 works. 4 works. 5 is missing, but 6 works. Right? Because when you cut 12 in half, you get 6. So 5 is missing. But if we just take 5 12s, well, now we're going to have a number that 5 definitely goes into. And that turns out to be 60, which is not going to be a coincidence that there is 60 minutes in an hour, 60 seconds in a minute, right? It's that way for a reason. The people who were figuring that shit out, who were not the Romans, who were not the Greeks, they knew something fundamental about how to deal with numbers in a pleasant way. And the morons who came up with the metric system didn't. They're just like, oh, we have 10 fingers, let's make everything 10. No, I mean, God, no. You also have, you can count 6 on this really easily too. It's not just 1, 2, 3, 4, 5. That's not the only way you can go about this. You could go 0, 1. So now we're counting like the arm. 2, 3, 4, 5, 6. Right? So the arm counts as something, and all of the fingers count as something. So each appendage off of the hand counts as 1. That is a perfectly reasonable way to do that, and now you have 12. Look at that. I'm holding up the same exact thing that you as a little child were taught means 10, but I just showed you that it can perfectly easily mean 12. And 12, as we just discussed, cooperates with more numbers than 10 does, so it's a better choice. These guys are like, oh, we have 10 fingers, so let's use base 10. Yeah, you're idiots in more than one way, right? We have established systems where we know that 12 is handy, and it's real close to 10, and we should have used that. Anyway, so kind of to get up to the scale, close to the scale of Avogadro's number, turns out if you take 60 and you raise it to the power of 12, that gets you relatively close. You're only off by a factor of about 277. You're about 277 times too small. About 277 times smaller than Avogadro's number, which sounds like a lot, but really, when you compare when you look at like how we handle distances on a human scale, on a normal human scale, um, take a meter, right? So that's half of a human body length ish, right? It's a normal size that humans deal with. And then you take a centimeter. That's like the width of your finger. That's also a normal human scale. Those are off by a factor of 100. And if you go down to a millimeter, which is still a perfectly visible size, and when you write, the line is narrower than a millimeter. So a millimeter is a perfectly fine scale to be operating with in conjunction with the meter. They're off by a factor of 1,000, which is about 3-4 times bigger than the difference between 60 to the 12th and Avogadro's number, that 277. So it really, for practical purposes, it's close enough, I would think. It'd be nicer if it was like maybe half, or absolutely, absolutely. But 60 to the 12th has some fantastic properties. All right, so 60, it's divisible by 10. So if you like base 10, 60 isn't too bad. It's also divisible by 3, which 10 is not. So you get this new fancy, we can divide by 3. And you can divide by 3 twice, because, well, no, you can divide by 2 times 3. Not by 3 2 times. But you can divide by 6, right? 60 divided by 6 would be 10. So it works pretty well with the base 10 thinking. 5 goes in there, 2 goes in there, right? All of the numbers, all the small numbers up to 6. 8 cooperates with it fairly nicely. 10 works with it perfectly. 12 works with it perfectly, right? So there's a lot of small numbers that work really well with 60. And when you multiply it together, so that's what the power is doing, you just amplify that effect, right? So 60 times 60, well, 100 now goes into that. 60 times 60 times 60, 1,000 goes into that, right? You get similar sorts of effects to raising 10 to a power, because internally that's kind of what you're doing. 60 is just 6 times 10. So like 60 to the third is 10 times 10 times 10 times 6 times 6 times 6. All right, so you got 3 6s multiplied together, 3 10s multiplied together. So that's 1,000. That's a number that everybody is used to. Right? It cooperates in some nice ways. And using 12 as your power, you get some nice features out of this. It's because 12 is divisible by 2. 60 to the 12th is a perfect square. And because 12 is divisible by 3, 60 to the 12th is a perfect cube. So if we want to make an object that has exactly this many particles, this many molecules in it, right? So say, I don't know, we want to make a little cube of silver. We can make that cube, theoretically, we could perfectly make that cube. One side length would just have 60 to the 4th power silver atoms in it. Done. And it's a cube, so all the sides have that many, and there you go. It's beautiful. There's no weirdness to it. It's not skewed, and, if you're using Avogadro's number, you can't do that. It's not a perfect cube. It's not a perfect square, right? You can't make a perfect square sheet of gold atoms with Avogadro's number. You can't make a perfect cube of silicon with Avogadro's number. It doesn't work. You're going to be off inherently, independent of any machining precision that you're failing at. You just can't, because the number doesn't cooperate with you. So I think this sort of approach, at least, something like 60 to the 12th. This is a really nice way to go into this and kind of use this as sort of our basis for developing everything else. And this is another criticism I have of the metric system. Avogadro's number doesn't show up anywhere else. Nothing else is based on it. It's just kind of like, yeah, there it is. And it's sort of a derived number, but then it's seen to be like foundational, or at least at some point in time it was. It's really weird. So yeah, kind of like my proposition is, not only do we define this number, we choose a number with really nice properties, and we define it intentionally, but we actually use it. We're going to use it everywhere. We're going to use it in every unit. And that's going to be really nice. Another thing that we're going to do is we're going to choose a material, a physically existing material, and we're going to derive all of our things from that. Originally, so like when I was originally thinking of this, I didn't think of 60 to the 12th. I thought of 12 to the 12th. But 60 to the 12th it's nicer. It comes closer to Avogadro's number by a pretty big margin, so it's, yeah, I think it's a better way to go. And it has some nicer properties, you know, it has better factors. It has more handy, convenient factors. So, yeah. But also, I was originally looking at hydrogen, but it then occurred to me as I was playing around with it, with, you know, this whole kind of concept of, once I kind of got into like analyzing the full unit system, that hydrogen has some really unfortunate properties. It has several isotopes which change its mass significantly, because fundamentally a proton is a hydrogen atom. And a proton with an electron is a hydrogen atom. And a proton with a neutron is a hydrogen atom. And a proton with a neutron with an electron is a hydrogen atom. And a proton with two neutrons is a hydrogen atom. And a proton with two neutrons and an electron is it's a hydrogen atom. Yeah, it's a mess. It's a mess. And the fact that a proton counts as a hydrogen atom kind of means that in a pretty real sense, hydrogen isn't actually even an element. You know, like a lone proton, is that actually an atom? It's ambiguous at best. So it just acts weird. It acts weird. It also likes to bind with everything, and it's really hard to get monatomic hydrogen. You know, it generally, if you have like hydrogen gas, it's H2, so it's two hydrogen atoms bonded together, which acts very strange. So one of the units that we're going to want to get to is temperature. And it would be really nice if we had a material that didn't do lots of phase change sorts of things. But hydrogen, even just around room temperature, so like above room temperature, you know, it acts, it accepts energy, its specific heat capacity acts like it's diatomic. But then once you get down below room temperature, it starts behaving like it's monatomic, even though it isn't, just because of its quantum properties. So even at kind of normal, everyday human experience sort of temperatures, hydrogen acts weird. Nah. So let's not work with hydrogen. Hydrogen's not great. But we just go one up, and we suddenly get something that's really, really nice. Really, really nice. So we go to helium. Helium is unambiguously an element. at least much more unambiguously an element than hydrogen is. It doesn't really like to interact with stuff. Being a noble gas, it's quite happy in isolation, just chilling. Um, there's not there's not a lot of variety in it. It's pretty much always going to be two protons, two neutrons, two electrons. Much more consistently than hydrogen is ever anything. Um, it's also it's some amount of it has existed since pretty much the creation of the universe. So it is a primordial element. So it's been around for, you can look anywhere, point a telescope anywhere at any time depth, and you'll find it. So it's really nice in that regard. It doesn't like to do anything other than be a gas or a plasma. So there's not much phase change stuff happening except in pretty high pressures and ridiculously low temperatures. So kind of normal physical regimes that you're going to find, outside of stars and just crazy situations. It behaves very consistently. So if we use it, it's still a small, simple element. It cooperates really nicely in a lot of ways. It has a spectral line, a very prominent spectral line, that it kind of looks like a sodium line. So sodium has two lines in the yellow, D1 and D2, and helium has one as well that's really close to that, and it was originally misidentified as sodium. But it was later recognized that actually this is something different, and it was first recognized in the sun. That's why it's helium, helios being like the Greek for sun. Yeah, so whatever. But it's still called D3 in reference to sodium, which is kind of fucked up. But whatever. History is it's that backwards compatibility bullshit that kind of plagues science. It makes sense. There's a context to it where it makes sense, but I mean, we know better now, so we could change it. Maybe you should. Anyway, yeah. So it has this really prominent spectral line, and there's not really any else around it. Helium has very clean spectrum. It doesn't, emission or absorption spectrum. It doesn't. There's not a lot going on with it. So I think that line, that very prominent line, that is a good thing to base things like frequency on, which we would use for determining distances and time. Right? Our unit for distance and our unit for time would be based on this. So my idea here is that your basic length, so that would be, comparable in concept to a centimeter, an inch, a meter, a yard, a mile, distance, the length. Basically, you would have 60 to the 12th of that wavelength, which is 587.49 nanometers. So 60 to the 12th of that distance, that would be, in my proposed system, that would be your basic fundamental length that everything would be kind of built upon. And your basic time would be how long it takes light to travel that far. So in this system, the speed of light is just 1. Right? Because its speed is distance on time, right? Like miles per hour. Miles divided by hours, distance on time. So your distance and your time, your fundamental distance and time units in my proposed system, they're the same numbers. Right? They're both 60 to the 12th times 587.49 nanometers. Both of them That's their number constituent, and then the rest is, the fact that one of them is a distance and the other one is a time. So the numbers divide off, all you have is 1. So your speed of light is 1 in this proposed system. So this isn't just a convenience anymore. So like, kind of in physics, when they set the speed of light to 1, it's really just a convenience. Because it is fantastically convenient to do that. But in my proposed system, it's actually not just a convenience. It's something that actually falls out of the way that we're approaching this in a principled manner. It is convenient, but it's happening for reasons, for much deeper philosophical reasons, right? We've thought our way to this point, instead of just being like, oh, here's some fucking crazy shit. Hey, wouldn't it be nice if we just used 1 here? That's not what's happening. That's not what's happening. And fundamentally, the reason that this is happening, the reason that speed is coming to be 1, is because space-time is a thing. Right? Space is measured with length. Time is measured with your time unit. So when you divide them, there should be, in some regard, commensurate. They should be able to mesh together, cooperate with each other. And that's exactly what happens in this system. And your speed of light just is 1. So we've got kind of our basic quantity sense. So like Avogadro's number, or mole, which we are using everywhere. And we have reasoned out a good number for this, something that makes sense. You could use any number you want. You can use something fucking terrible, like some 47,000 digit prime number if you're just an asshole. Go ahead. It doesn't matter, but something with whatever. I went over it earlier. So we've got our basic number. We've worked out that we should base stuff on helium. We've worked out what our length and time should look like. So now, kind of the next one, it'd be mass is the one that I have listed here. Is the next one. So that would be like grams, kilograms, right? So basically, we just take our fundamental number, 60 to the 12th power, or whatever you choose for it to be. And just take the mass of helium, and there you go. There's your basic mass unit. Easy. So, that would be 60 to the 12th times 4.002622 Daltons. Okay. Done. Now, this next part becomes really, really nice. Really, really nice. So if you thought maybe like I was doing some magic trick there where I got c to be 1, speed of light to be 1, this will probably just break your brain. Okay, so thinking about gravity. So okay, one of the fundamental units in the metric system relates to electricity. So I think there should be a fundamental unit that relates to gravity, because that is also a fundamental interaction, right? Okay, so gravity. What does gravity affect? Gravity affects everything with energy. Mass, no mass. If it has energy, gravity affects it, right? So, me, I'm heavy. Gravity affects me. A photon, not heavy, has 0 mass. Gravity still affects it, right? You still have gravitational lensing effects. right? Where light bends around massive objects. So, really, the fundamental unit of gravity is energy, because anything with energy, it's not mass. It's not mass. It's energy, right? If it were mass, photons would be unaffected, and it would not be possible to detect dark matter via light if the units that gravity works in was mass, because photons don't have mass, but they do have energy, right? And that energy of a photon, it's basically, it's related to the wavelength, and that's pretty much what it is. It's related to the wavelength, and you get momentum out of that, and that's how you find the energy. Whereas, for me, you just throw me on a scale, and you're like, oh, yep, that's how massive you are. It's your rest mass. Good times. So something nice happens here. When we look at how energy is, the units for energy, so the joule in metric, units for energy are derived in systems like metric or imperial. You get, what is it? It's mass times the quantity distance over time, so speed squared. Okay. Well, when we take, in our system, when we take distance over time, when we take just one unit of distance and one unit of time, divide them by each other, you just get 1. And it's the speed of light. And when you square that, well, you're going to get, speed of light is c, so you're going to get c squared. And that's going to be multiplied by a mass. So suddenly this looks familiar. E equals mc squared. That's kind of nice. Okay, maybe we're getting somewhere with this. This is interesting. Yeah, but our c is 1 in our system. So when you square that, it's still 1. And when you multiply by that, you can kind of just ignore it. So really, what we have done is we have established a system of units where your fundamental unit of energy and your fundamental unit of mass are identical. Basically, what we just did is we made a unit system where it looks like the fundamental unit for gravity should be mass, even though it's actually energy. It makes it really hard to tell them apart. And intuitively, just naively thinking about it, you would probably think that the fundamental unit for gravity should be mass. So I don't know. I think this is fantastically beautiful at this point. Much cleaner, much more elegant than metric. And we thought it through from the beginning, right? Yeah. So getting to the temperature thing, I don't know. I think I briefly mentioned this, but so kelvins would be the basic unit for temperature in metric. My idea is, okay, so we're basing stuff on helium. Helium has this really nice property that it just kind of wants to be a gas and not really anything else, right? You have to put it under pressure and very low temperatures to get it to really do much of anything else. So yeah, it wants to be a gas. So you don't get phase changes that kind of screw up how you could measure temperature with it. So basically what you could do is you could set up a temperature scale that is based on the changes in helium, the change in the properties of helium, as when you add a certain amount of energy to it. right? So you'd have like a set volume of helium, and you'd add a certain amount of energy to it, and what it jumps up to, that's a degree. And it doesn't matter where we are within a very wide range, right? And what this is going to do is it's going to give you a temperature scale that is, at least for a real substance that actually exists in the universe, isn't curved. And this isn't how any temperature scale that exists works. All temperature scales that exist, at least that I know of, are curved for every substance. So you have to know the specific heat capacity for whatever thing you're talking about always. There is no material where you can ignore its specific heat capacity. And it changes at lower temperatures, higher temperatures, and when there's a phase change, it gets all fucked up, right? What actually basing the system on helium and taking points over a very wide range, from very, very cold down to 1 Kelvin, all up to temperatures just shy, where helium wants to become a plasma. Looking at it and okay, we dump this much energy into it, and it gets this much warmer. That's a degree at this point. 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 And now you've defined a very clean, meaningful, physically meaningful temperature scale. It's not going to be highly divergent from a Kelvin system, but kind of away from ordinary living temperatures. It is going to diverge. Right, because, yeah. Basically, the scales that we use were, for the most part, based on how water behaves. And, like, liquid water, which kind of exists over a narrow range, and even over that range it behaves differently when it's close to freezing compared to when it's close to boiling. Its specific heat changes fairly radically over that, but these scales were generally set up linearly, right? So we're assuming a linear progression, and when it's not a linear progression, so the curve is just fucked up everywhere. Like, we're not looking beyond this small range, so it does crazy shit. You get, Bose and Einstein looking at really cold temperatures. It's just like, what the hell? There's some crazy shit happening here. Down at these low, 20 kelvins or some shit. It's just like, there's some weird shit happening. That's an effect of this. That the temperature system that we have is just not set up right. It's not set. It doesn't reference anything. It doesn't actually reference anything. It takes the naive assumption that we can take this temperature and we can take this temperature and then just divide it up linearly and then extend that forever and it'll work. And to a degree, it does work. It's it's useful, but it's curved for every substance that exists. So you have to understand the specific heat capacity of every substance, kind of at every temperature, which is really fucking annoying, I would imagine. Having played with this a little bit myself, it's always been annoying for me, and I don't even have to do this very often, so, whatever. Yeah, and kind of like I mentioned, there should be the fundamental unit for electricity should be a charge. It should be the charge of the electron, or something like that, or some number of those charges. So our 60 to the 12th power number of those charges, right? So that many not electron volts, that many E. Yeah. There should also be a unit for the strong force. So I don't know that for that one you can't really get more than a few of them together at once. I don't think. I'm not sure about that one, but really you should have ideally a fundamental unit for each of the fundamental interactions. So electromagnetism, you get the electron charge on the electron. The color, I think it would be for the strong interaction. And electroweak also, it's basically, yeah, electromagnetism, electroweak, because the W boson, it has plus or minus the electron charge. So that seems to kind of be it for that. I'm not sure. I don't deeply understand how that works, so whatever. But certainly the charge of an electron. Something for the strong force. The color charge makes sense, I think. And then something for gravity. So there's all of your. So we have one of them is electro weak. That's why there's not four. Electro weak, strong, gravitational, and the gravitational is beautifully mass and energy converge on the same thing. They are different units, but the value, the size, the way that you would calculate, the numerical value of it, turns out to be identical, which is really that's lovely. The same thing with distance and time. They end up looking very similar, which is also very lovely. That agrees with not only like the relativities, where space time is this thing, and time and space just kind of like merge into each other under certain conditions, but it also agrees with just ordinary experience, where basically every language, to some degree, you can talk about a time as a distance or a distance as a time, right? So a long time ago, I took a long walk, right? You're using the same term. It was a short time. He's a short person. It's the same term. One is referring to a distance and one is referring to a time. Like, we do this normally, automatically. Why? Well, I think it's fundamentally because the way that you measure time and distance is really the same. It's really the same. Like, you kind of measure time by how long does it take you to go that far, and you kind of measure distance by, well, how far can you go in this amount of time? Like, they work back and forth, even at an intuitive human level, let alone the like grand general relativity, special relativity level. So, I think it's really nice that this automatically just falls out of kind of the way that I was thinking about how an ideal sort of unit system would work. I don't know. I think it's quite lovely in quite a few regards.